All right. Hi, everyone, and welcome to our 15th webinar in our first webinar series as a part of ESCOM. ESCOM is the Eastern Shore Citizen Science Coastal Ocean Monitoring Program, and we, as a group of citizen scientists that live along the eastern shore of Nova Scotia and Canada, help monitor the beaches. So we monitor various things on these beaches. We have our weather stations, help us monitor wind speeds, weather events. We have beach profile, looking at the slope of the beach. We have beach flora, but we also have a new parameter that we're going to be introducing called granulometry. Granulometry is a big word, honestly, but today we have our wonderful guest speaker, Dr. Enzo Pranzini, to help break it down for us. He was formerly the full professor of physical geography at the University of Florence and a past president of a national group for coastal environmental research. And he spent 50 years working on issues related to coastal erosion and shore protection. He'll be talking to us today about the importance of the sand and the rocks that we have on our beaches, as well as why we should care about it. So, Dr. Pranzini, thank you so much for coming to talk to us.
Well, thank you very much for inviting me, and much more for inviting me directly in person in Canada. And so I can see your beautiful white sand, fine sand beaches. The problem we have today is this is sand or sand. It seems the same, but you will see during the presentation that these two words have a different meaning. This is fine sand or fine sand. Again, the same problem. This is a sandy beach, but it's not a sandy beach. Why? Because if we classify these sediments, it's not sand. It's not fine sand, they are granules. But when we go on the beaches, we don't care of this. Generally, we say, we walk on the sand, and this is quite normal and quite frequent. But sometimes walking on the sand with naked foot, we realize that it's not really sand. Sometimes it's coarser material, it's gravel, like this. This is a gravel beach. We shall see that at the end. It's a nourished beach with gravel. And here it's very hard to walk on this sand. And obviously nobody will call this sand, but you call pebble or maybe coarse gravel, it depends. When we go on the beach, we generally think we understand, we realize which is the sediments. Here we are in Skagen, in the northern Denmark, and everybody thinks that this is gravel or small pebbles. However, walking on the crest, I let some boulders to fall down, and I realized that beneath there is sand. So this is a mixed sand and gravel beaches, but I see only sand because wind erode the sand component, deposit it in the dunes. And you see my arrows? Camillo, do you see the arrows?
Yes.
Oh, okay. Because in some programs we don't see the pointer. Okay, so this on the surface is a very flat here surface of coarse material, but beneath there is a lot of sand. And like here on the Schwartz zone, you see that there is a mixed sediment. So just starting and trying to classify these sediments, it's very difficult. It's very difficult to take a sample, a significant sample, and it's very difficult to analyze this. Very frequently, beaches see sediments separated by wave energy. Here you see gravel, you see cusp of gravel, small cusp of gravel, but you see sand beneath, and you see sand on the upper part of the beach. So if I had to take a sample here, I don't know where to take it. I could also take hundreds of samples, but I don't know which is representative of this beach. Here you have a beach where there is a very strong separation between sand, let's say sand, general sand, and pebbles. Why? Because in the system there is a bimodal distribution of sediments, and strong waves bring coarse material in the upper part, but during the day, during the year, most of the time you have sand. Also here, it's very difficult to say which is the characteristic sediments of this beach. And then if you have sand on the top, you can dig a hole and you see that there are very layers here and layers also here. Each of these layers represent an erosive or a sedimentary event. In this case, I should take not only hundreds of samples on the top of the beach, on the top of the surface, but also I should make many cores and take samples at different levels. So you see, it's a very complicated thing. Here we are in a beach in India. Here, this is quite fine sand, and you see the beach slope, the dry beach slope is quite mild. Here we are in a gravel beach, and the slope is much more strong. So we realized that there is some relationship between the dimension of the sediments and the profile of the beach. Generally, we see only the upper part of the beach. We don't see the submerged profiles. We shall see that looking down in the water, we find much more problems. So the general consideration is this. You can see, increasing the grain size, I have an increase in the Schwartz zone slope. So coarser materials gives the beach a very strong slope. But there is another variable. When you have a big storm, even if the beach was steep, it becomes with low slope, much more mild, because there is this relationship. Increasing the wave energy, you have a milder slope. Why? I explain in this way. If you have a milder beach, the surface on which waves dissipate energy is larger. And so there is a reduction of energy for each part of the beach. This is a system in which the beach adapts to absorb the wave energy. So let's start again from this general relationship. You see dimension here are not 1, 2, 3, but are, let's say, exponential. We shall see why. Starting from this relationship between beach slope and grain size, we have that if you have lower energy, we have an increase in the slope, in the angle of the Schwartz zone. If a storm arrives, we have a reduction of the slope. We have a milder profile, which can better dissipate on a wider surface the wave energy. So just this show you that, let's say, day by day, the morphology of the beach changes and can change very much. I represent this concept in this way. It's not a graph. You just have, this is bigger grains of sand, and you see it is in a very slope profile. And so the very steeper, and fine sand gives a milder profile. So it's not a real graph. It's a graphical representation of what you see. Coarser material, steep slope, finer material, milder slope. When waves arrives, strong waves produce a flat profile. You see here, small waves produce a steeper profile. So let's go on a beach. Here we are in Llandudno in Wales. It's where It was written Alice in Wonderland. These boulders, this pebble is 9 centimeters. This is 8 centimeters. There is 1 centimeter of difference. Is it a big difference or not a big difference? Let's go in the beach we have seen before. This is 1 centimeter. This is 2 centimeters. The difference is again 1 centimeter. But I suppose that these are much more different than the previous one, even if the difference is the same. Okay, let's take 2 spheres or 2 pebbles, 10 centimeter and 10 centimeter 0.1 millimeter. They have 1 millimeter in difference, okay? I let them go in the water and they reach the bottom in the same time. I take 2 grains, the difference in dimension is the same as before, 1 millimeter. But in this case, the one which is just 1 millimeter larger arrives to the bottom before. So you realize that the difference is not important if we don't say around which values the difference is. That's why when we measure the sides of the sand, we consider that we are interested in sand moving in the water. We are interested in the falling velocity of the grains. So 2 boulders, we are on the top of the scale, which have very small difference, 1 millimeter, they are considered the same as hydraulic point of view. But finer sand, 1 millimeter different is very big difference, and their behavior is completely different. So we must make a classification of sediments considering this. So we have classes which are very small in millimeter when we are with sand and fine sand, and the classes are larger when we are in coarser material. Now you understand why before I said, is this sand or sand? The difference was that in the second case, sand was written in italic, which is the difference. When we talk, we are in the bar drinking a beer, we say, this is a sandy beach. But if we measure the sand and we classify the sand, we must explain that the term we use derives from a measurements, and it is within a classification. So if you write fine sand, you must also say that is considered fine sand according to Wentworth classification. So this is the difference. We generally talk of, without referring to this, of course, but when you write, if you want to say that you measured the sand and it's exactly that dimension, you must write it in italic and explain at the first time you mention the dimension in which classification you are working. So this classification, you see, it's quite unusual because the gap between among one class are very small when we are in clay, in silt, and the gap, the interval, becomes larger. This is a scale which is based on a logarithmic consideration. It's the logarithmic in base 2. I'm sure that some of you do not remember what is a logarithmic in scale 2, but never mind. Let's start considering the value, and we start from 1 millimeter. I ask you, and maybe you remember, which is the length of the diagonal of this square? Probably you remember the root square of 2, which is 1.41. This is from the primary school, probably. So this is a logarithmic scale in base 2. So the next step is 1.41, the dimension. And here again, if this is 1.41, how much is this? This is 2. And how much is the diagonal of the square in which a side is 2? It's 2.8, which is the double of this value, and go on. This is the scale in phi, and the limit of the different classes that you will use, surely, growing from 1 millimeter. Okay, if we have finer sediments, if the square is 0.71, his diameter is 1 millimeter. So going down with the dimension from 1 millimeter, 0.41, and then we have 0.5, 0.35, look, that is half of this value, and so on. So if I go back and we look at this scale, you see that we find the same values, but not exactly the same. You see here 1, 2. Before we had 1 and 1.41, because the scale we were using is half of this interval. The interval in this way is expressed in phi dimensions. So these are the dimension in phi. Only one problem. Someone decided that since we generally study sand or fine sediments, they suggested to introduce a negative value. That's why when you have coarser material, you have a negative phi value. But I don't say you can forget it, because when you describe a sediment, you must know this. But from the conceptual point of view, it has no meaning. So, okay. Then we said that when we take a sample, surely not all the sample is composed of the same size of grains. Probably there is a class of grains, a group of grains which are very similar, but in the same sample, there is some coarser material, coarser grain, and finer grains. So maybe you know this way of representing data. You see that in this case, 2 millimeter, which is 0.5, 2 phi, which is 0.5 millimeter, has approximately 20% in weight, let's say in volume of the sand. But there is also coarser material, you see negative values, and finer materials. I must represent this. So I will say that I have a mean size, which is approximately, let's say, this value here. But then I must explain how much they are different, the grains inside the same sample. And this is expressed in sorting. I don't want to explain this. Maybe you can have, or maybe you know that from statistics also. But I just want to say that when we see a sample, we must understand, we must measure which is the mean size, but also which is a sorting. Because in my samples, I can have grains all of the same dimension, but I can have gravel and sand and pebbles all together. I must say this. This is a case of a grain size distribution of a sand. You see, this is again in phi, this is 1 millimeter, This is 2 millimeter, this is 4, this is 8, this is 16 millimeters, sorry. So you see that there is a bimodal distribution. We have medium sand here, but there is a tail of coarser material, and in this case also of gravel. Let's go on a beach. This is a beach in Tuscany. I take a sample on the dry beach here, and I have this distribution. Here I put dimension in millimeters. You see, the most frequent class is that of 0.25 millimeters, but I have grains of 4 millimeters, 8 millimeters. But if I take the sample on the dune, I find this. First of all, the mean size is smaller and the sorting is better. Why? Because wind blowing on the beach take out the finer sediments and deposit them on the dune. So the beach remain with coarser material and unsorted. The dune is finer and better sorted. When a river brings sediments to the river mouth, waves move sediment along shore. And walking along shore, generally I find changes in dimensions. If this is my beach, you see that walking from here, from left to right, I find coarser material. This material is reducing in size. When I arrive here, I have fine sediments, fine sand, let's say, in italic. Okay, but when I go on, I go the other side, the sediment size increases. Why I have this? Very likely, I have sediments coming from two sources, from the left and from the side, and this is a convergence zone. While moving, sediments lose the coarser components and they, for abrasion, reduce the grain size. But the reduction that I see is mostly due to the selection in the transport than in the abrasion of the grains. So you can say that sediments come from the right side in this part of the beach. And this is quite important because, let's say, if you want to build a harbor here, you must know that this harbor will intercept the sediment coming from the left and will create erosion in this part. So also for application, it's very important. But also here you see the difference. Near the source of the sediments, you have very unsorted sediments, coarser material together with finer material. But while moving, I have the selection of the materials and I have an increase in sorting. So here you have finer sediments and better sorted. So you see that these two textural parameters can teach us from where sediments arrive and which is the effect of any work I will do on the beach. But we have seen that beaches, sediments do not mix. This is a case which occurred in southern Italy. They put gravel in a sandy beach because they wanted to protect this terrace here. They supposed that gravel could be covered by sand, that gravel could infiltrate in the sand body and it discharge a cheap material like gravel, and on the surface you have much more expensive material, which is sand. This did not happen because gravel is floating on the sand. Gravel generally remains on the upper part of the beach, and we can also say that waves like a bulldozer push the gravel in the upper part. If you put gravel in the sword zone, generally it moves upward. If you go swimming in a beach, which on the dry beach you have gravel and sand, when you have 1 or 2 meters of water depth, your foot generally are only on sand. You don't feel coarser material, because coarser material is accumulated in the upper part of the profile. This line of gravel moved in few years for several kilometers. But we always discuss and we always say sediment on the beach, considering only the dry beach. But if we go deeper, we find completely different things. This is, let's say, a coarse material. You see, this is a graph in which you have the water depth or upper part of the beach, 1 meters up, and you go down up to 4 meters depth. When the upper part of the beach is finer, because wind blown has taken this sediment and put them on the upper part. This wash zone has very different grain size, but the coarsest material, you find it at 1 meter water depth. This is the step. When you enter in the water, generally you have a step, and in that step you have generally the coarsest material of the beach. Then when you go deeper, you see just at 2 meters, you have fine sand. You don't have gravel or pebbles. So there is a very strong separation of material along the beach profile. I skip the other side. Look at these beaches, this bay. We are at Elba Island. And here these things are easier. They are much more simple. You have the upper part of the beach, which is medium sand. But if you go in the step, you have very different material, also coarse material. Then you see that going down, you have a gradual reduction inside. Remember that negative values are coarser material. So this material is finer than this. And you see there is a trend. Generally, going offshore, you find always finer sediments. This is one of the reasons for which beach nourishment done by material taken in the near shore do not remain for a long time, because in the near shore you have finer sediments than those present on the dry beach. So if you take that sediments from, let's say, 5 meters water depth and you put them on the dry beach, they will return to their home. So they will immediately, with the first storms, return to the deeper part of the beach. That's why, we shall see later, we generally try to make beach nourishment with coarser material. Another beach, we are again at Elba Island. Look, that is a bay which is quite closed. And look, this is the profile, the water line. We start from 1 meter up and we go down. Here we have a bar and so. Look at the sediment sides starting from the upper part of the beach. We have a reduction in sediment sides, and at the same time point, the dimension grow again. This is quite unusual, because I told you the deeper you go, the finer sediments you find. But look where we are. Here, this material is this one. So I have, exiting the bay, I meet higher energy, which comes from sea, which is oblique to the bay. So I have at the beginning of the reduction in sediment size, according to the law that we have said before. But when I go outside the bay, in this case, I have an increase in sediments. In this case, the local administration made a mistake because they dredged sediment here to make the nourishment. So they took the finer sediment in the bay, whereas if they went a bit offshore, they could find coarser material, even coarser than that present on the beach. Here you see a difference. We are in Liguria. These are triple files on which we took sediments. And you see here, we have coarser material here. Look, I have millimeters here, not only feet, but you have a very strong separation of the sediments offshore. This is very interesting for us because I realize that if I make a nourishment with material of this dimension, these sediments will never move to this water depth. So I will not lose the sediments. They will remain in this area, which is the upper part, the profile, or close to the swath zone. Just a question. Do you follow me? Is it clear? Silence. Okay. Thank you. Well, now we have seen beaches without any shore protection structures. We know that shore protection structures modify the morphology of a beach. For instance, when you have a groin, everybody realized that on the updrift side, you have a wider beach, whereas on the downdrift side, you have erosion and a smaller beach. This is a morphological response of the beach to the inclusion of a groin. But let's consider the sediment. If you have a short groin, these intercept only the coarser material, because we have seen that gravel moves only very close to the swath zone. So in this case, only the finer sediments can overpass the groin, and you will have a wider gravel beach on the one side and a sandy beach on the other side. So you have a grain side separation. It's like a sieve. And actually, we had once a project in which we used the groins like a sieving machine, because we had coarser and unsorted material to discharge on the beach, and we decided to put all together and built a small groin at the beginning, which was stopping the movement of coarser part, then a bit longer material which was stopping all the gravel, and then the sand was moving in the other part. So we were sieving the grain, the sand or the material, the aggregates, using the different length of the grain. But if we go, sorry, I have this and I can, okay. But if the groin is very, very long, and also fine sand cannot overpass the tip of the groin, what happened in the other side? On the other side, we have only erosion. And erosion is a selective process which take off the finer components. In this case, in the eroded part of the beach, I have very coarse material because it is a lag deposit of the original unsorted material. So you see the difference of the groin make the downdrift beach completely different. And we can work on this when we make a project. You see here, this is a groin which has been disconnected by erosion, but you see that on this side you have mostly gravel, and in this side you don't have it, or you have very little. This means that sediments are moving from the left to the right. So you have a selection in grain sites. If you have a seawall, a wall on the beach, you have wave energy. We have reflection of waves on the wall. You have very high turbulence. Fine sediments are continuously in suspension, and they are taken away by the waves. In this case, in front of the wall, generally you have coarser material, like in the photograph. Let's take another kind of structure, detached breakwaters. Detached breakwaters collect sand due to the diffraction of waves on the tip of the structures, and the diffraction make wave rotate, and rotated waves arrive oblique to the beach and push sediments on the sheltered areas. Okay, but which are the sediments which moves in this case? Obviously, the finest sediments. In addition, here you have less energy than here, so you have sedimentation of fine material. In front of the gaps between the structure, you can have a bit coarser material. However, generally, this is a very low energy area with fine sedimentation. But it's fine sedimentation also because only fines can arrive here. Well, don't look at this table. Look only the profiles. This is Dean law, which says which is the shape of the beach profile following the dimension of the grains. Let's take this case, sand of 0.1 millimeter. Let's say fine sand, 1 meter far from the shoreline, you have 1 meter of water depth. If at the same distance you have a coarser material, 1 millimeter, you see that you have more than 4 meters. So you see that the difference in the slope following grain sides is not only in the swash zone, but it's also and much more in the submerged profile. So look, obviously the scale is not different. These are not the real slope. However, there is a very big difference. And when you have a coarse material, the beach generally, when you enter in the water, after a few meters, you must swim because it's very deep. When you have very fine sand, you can walk many and many meters before starting to swim. This is a quite important thing because we use this concept when we make big nourishment. Here there are two beaches, one fine sand, very mild slope. This is a gravel or pebble beaches, which is very steep. Let's apply this concept when we make a nourishment. If I have the profile of a beach and I nourish this beach with fine sediments, the beach profile will become much more mild. And you see that most of the material I put on the beach goes in the near shore. And my beach has a very little expansion. In Italy, we can say we can put very few umbrella on this beach. But if you use coarser material, the coarser material has a much more steep profile, and you see that most of the sediments I put remains near the old shorelines, and the dry beach expansion is much more important. So with the same volume of sediments, if sediments are fine, I have a very small beach expansion. If sediments are coarser, I have a very big expansion. And this is very important, much more if I have this beach nourishment for coastal protection, not for tourist protection. So we start a conflict because concessionaires of the beaches in Italy want fine sand to put much more umbrella, but they will lose this sand very soon. If we want to protect the property behind the beach, we must use coarser material. Here is a nourishment we have done recently, dredging the sediments in this area, out of this headland. Sediments was a little finer than the native sediments. And generally we try not to do this because we said that if I put sediment finer, they are unstable and my nourishment is lost very soon. But we must also consider the cost. In Italy now, if I take sand from quarries, I pay, let's say in dollars, $90 for cubic meter. If I dredge sediments here, I pay 30 or something less. This means that paying 1/3, I can put 3 times the volume. So in this case, if sediments are a bit smaller, I will lose them before, but I have a bigger volume to put. So there is also a cost-benefit consideration. Here you see another nourishment. I did not follow this one. Again, this is very fine sand. You see, when it arrives, it's very dark because it's rich of organic matter, the sediments taken in the near shore, in the offshore. But soon after, with the sun, with the air, we have oxidation of the material, and you have the original color of the grains in that area. This is a nourishment we have done, say, more than 20 years ago. And if you go on Google Earth, you still find this sand there. But there is, you see, there was not a beach. These stones are approximately this one. And you see, there was not a beach here. We created a beach only because people going to this tourist village, to find the beach, they were taking boats in the harbor and going in a beach which was in a protected area, which not support a very strong invasion of tourists. So the region decided to create a new beach in front of the village to host these people for most of their time in the holiday. Then 1 or 2 days, they go to the other beach and see a very beautiful landscape. Well, we made this nourishment with gravel, with granules, let's say, not real gravel, 1, 2, 3, 4 millimeters. Here is another case. This is the beach we have seen before. We said it's a gravel beach. This is from Google Earth. This is the beach as it was before. You see, there was no sand. It was a very dangerous place where to go. And there was the need to create a beach and to recreate a beach. The problem is this, that without very strong, hard protections, sand was not stable here. So if I put sand here, I had to make a detached breakwater closing completely the bay with a very bad impact on the landscape, on the water quality and so on. So the decision was to make a gravel beach, which is very stable. Take care, gravel beach is stable not because gravel are coarser and are much more weight than sand. The reason is that gravel has a very high porosity and permeability. So when you have the uprush on the source zone, you have a very strong water infiltration, and the backwash is very reduced. This makes the beach stable, but creates a very high berm because the accumulation is in the very upper part of the beach, and the backwash do not bring the sediments back. However, you see that we make this. This beach again is approximately, let's say, 15 years that is here, and it's approximately of the same dimension. This is the last example that I want to show you because it's a very crazy experiment. We are in Marina di Pisa, which is the new town of Pisa, which was built at the end of the 19th century, just when the beach was eroding. So they make a wrong project. So they had to defend the village with detached breakwaters, the seawalls, revetments, and so on. We had to change this landscape. We wanted to change this landscape for many reasons that I will not explain now. And what we made, here we have 10 detached breakwaters. We are at the end of the detached breakwater. There is only a revetment. We made a gravel beach there, and this beach remained quite stable. So we decided to lower these breakwaters to the sea level. In this case, we had less reflection of waves in front of the breakwaters, and the reflection of the waves was eroding the bottom, was lowering the profile, and we wanted to rise the profile. So we lowered this. Obviously, wave energy arriving here was stronger. So we decided to absorb this wave energy with a gravel beach. And this is the landscape you see now. There is no more the emergent breakwater. You see only the breakers on the shoals that remained, and you have a gravel beach. Considering the cost of this, there was the original project of the ministry who wanted to rise these 3.5 meters, so closing completely the view from the village, and the cost was 3.1 million. And this project created a wide beach, although of course material, and costed only 2 million. This is the cost for kilometer of cost. So in this case, the use of gravel, using the characteristic of the gravel, which absorb the energy, so we could give a different landscape to this village. So that's all. I hope you understand all better. I hope I explained well the things so that you could understand them.
Thank you so much for giving us this talk, Enzo. That was really interesting.
Thank you.
I'm going to start on questions now. Marianne, you had your hand raised.
I don't see the...
That was an accidental hand raise.
Oh, don't worry about it. Here, I can lower your hand. And any questions, if anyone has them, can be put in the chat. But I'll just read out the ones.
I don't see the chat.
You can see them? Okay, awesome. If you just want to read out the questions before you answer them, that would be great.
Let me see, I close this. Okay, where is the chat? I don't find the chat.
I can read out the questions.
Okay.
If you'd like.
Slowly.
No worries. Of course. The first question, what is the effect of seawalls on granulometry? They're quite popular in Nova Scotia as a coastal protection structure.
And we have seen that generally in front of the seawall, you have higher energy because on a natural beach, you have a wide surface on which waves dissipate their energy. But when waves arrive to the seawall, there is the water in contact, and so there is no dissipation, but there is very high energy, there is very high turbulence, and then there is the reflection of the waves on the seawall. So the turbulence make sediment in suspension, obviously much more fine sediments, and the reflection push these sediments offshore. So you have, first of all, a deepening of the profile in front of the seawall, a coarsening on material, and generally offshore, a bit offshore of the seawall, you have a sandbar, because it's where the incoming waves meet the reflected waves. And then you have the deposition of the sand eroded in front of the seawall. This is obviously a general, very general concept of fault. Then you can have much more factors influencing this. However, this scheme is quite general, but it's reasonable.
All right, thank you. How could the size of sediments change with the seasons, with winter or summer seasons?
Yes, let's say generally we were using the term summer and winter profile and summer and winter grain size. Then this way of describing this change is not more used in the literature, the scientific literature, because we prefer to use storm and swell profile, considering storm very high energy and eroding process, and swell is a milder wave, a constructive waves. So in this case, we have the opposite of what generally we think. And we have been thinking, also me have been thinking for a lot of time. We said generally, when you have mixed sediment, because you must start from mixed sediment, because if you have uniform sediments, you have no changes, of course. If you have mixed sediment, generally we are telling, when there is a storm, gravel remain to absorb the wave energy, because gravel is better for this. But when we go on the beach, and I have a colleague who for many years from his terrace looking the beach shoot photographs, and he realized really that during a very big storm, every mixed sediment beach is a sandy beach. While when you have calm weather, constructive wave create a barrier, let's say a crest of gravel on the beach. So it's the opposite of what generally we think. This, at least in the areas we study.
Lorraine, go ahead.
Yeah, in Nova Scotia, it seems that the beaches in the wintertime, when the big storms come, we end up with boulders. The beaches are covered in boulders. We don't get the sand back until about midsummer.
You have sand so you have sand in summer and boulders in winter.
Yeah.
This is another reason for me to come to you.
Yeah,
I wonder if that's related to ice, Lorraine.
possibly. But no, because it's the ocean, it's the beaches that face the ocean that are right out on the ocean that end up being like Lawrencetown Beach ends up, it is totally rocky. It has a good dune system behind it, but the beach becomes totally rock over the winter storms.
But so, I must say that maybe that the sandy component of your beaches is the minority compared with the rocky components. In this case, maybe that the beach cannot acquire the milder profile. Obviously, higher energy and reflection of coarser material can push finer sediment, of course. In this case, I think there is also the component of reflection. Consider that a gravel beach, a coarse beach, being steeper, it's much more reflective. So maybe that in your cases, the reflection component is higher than the difference in absorbing the wave energy by the beach. That I told before we were considering a coarser material coherent with stronger energy, but experiment observation is changing our mind. But the original idea probably have some reason to exist, and maybe that there are beaches having different behavior. I suppose, obviously, it's according to the wave energy, to the characteristic of the wave, but also maybe in the component. If there is few sand, obviously, this sand cannot create a profile to absorb the wave energy, and the reflection push this sand offshore. And milder waves, generally it's constructive, and maybe this sand return. Since you are measuring grain size in these beaches, I think this is an observation which is very interesting, and you can collect data, and when you have some data, we can meet again, and I'm very interested in looking and discussing with you this data.
Yeah, I would like to add just a comment related with that, because I think Lawrencetown Beach, that is the beach that Lorraine is talking about, is quite interesting in the sense that, just also for the people that are here in Nova Scotia and can visit the beach, you will discover that this beach is a sandy beach in the sense that Enzo explained, because it has always sand, but it's covered by gravel, and even gravel and even pebbles. I don't think that it's boulders, and they are not too big, but they are gravel and pebbles, but they are over the sand. And one of the evidence that we have that there is a sandy beach is exactly as Lorraine said. There are dunes behind the beach, so it's like we have all the sand and these pebbles and this gravel at the top, and it shows that this is a sandy beach that is experimenting the difference between we can call the winter profile or the storm profile, but we used to have the storms during winter, so maybe this is why this relation is when we have more energy, more waves, bigger waves, so we have more energy, and this is why we have these look like a rocky beach. But at the end of the summer, when we had all this swell, when all these gently waves, we have a more sandy beach from the perspective. And this is why we want in ESCOM, we want to start measuring the different granulometry, the sediments in three different points, from the upper part to the middle, and the berm, and close to the waves, so that we can in the future identify how it is changing also with the beach profile. But this is just a general comment about Lawrencetown Beach, that is a quite common kind of beach here in Nova Scotia.
Yeah. Is it possible that the wind component is part of this selection? Is it possible that during winter, if you have strong wind, the sand is moved and remains the gravel in the upper part of the beach, and it's not only the selection by waves, but also by wind?
Yeah, it could be, because we have here very strong winds, one of the strongest of the world, especially here on the eastern shore. So it could be also a selection by winds, totally. And this is just to make some advertising. Yeah. This is why also it's important that we have weather stations, because if we have weather stations, we have beach profiles, and we have this granulometry analysis, we can cross these different variables and try to understand better. So it's not just one parameter, it's that we have different parameters. And also we have now some wave gauges with some sensors.
Oh.
So in the future, we're going to have the measurement from waves, from wind, from beach profile, and from sediments. So ideally, we can explain quite, a lot better what's happening in each of our beaches.
It's a good laboratory.
Yeah. I think, Chris, you have a question.
Another reason again to come there.
Yeah, it was less a question and more a comment. Oops, I'll turn my camera on. To echo what Lorraine had said about in the wintertime, the loss of the sand, and then the summertime, the sand has come back. So a few years ago, we had some big storm systems come through, and we had a crazy amount of sand disappear. Very large stones, boulders appear where there was sand. And now over the summer, over this winter, the storms haven't been so bad, and we haven't seen any of that reappear. So it's the sand went away, and then the sand's back. And I think it's really a more function of the storms that are hitting than the wind per se. But one of the things we're seeing in Clam Harbor Beach is the kind of the ends of the beach where you've got sand disappearing. In the middle, certainly there was sand gone, but there was the sand. It continued to be sand. It didn't get down to a layer where there were large boulders. So it's interesting to kind of take this perspective, and then to add granulometry, if that's how that's pronounced, to that, to maybe do a little bit of analysis of kind of that the sediment that you've got in conjunction with the storms. Maybe there's some prediction of what's going to happen or what isn't going to happen based on that understanding. So anyway, more of a comment than a question.
From what you say, I imagine a beach different from those I know, in which you have a lot of rocks, boulders, a few sand. In this case, when there is a storm and the beach wants to acquire a milder profile for a beach means to move sediments from the worst zone to deeper part of the profile. But if there is only sand which can be moved, I imagine that really sand moves offshore, preventing the beach from any sediment except the boulders, which cannot be considered a dynamic part of the beach because they are too big to be moved. So maybe that it's a very not unusual, probably there is thousands of beaches like this in the world, but in this case, since during the storm, the beach is not steep, not to be steep means to move sediments offshore. And the only sediments available are the few sand that there is. This sand moves offshore, and you have a milder profile, but remains boulder exposed to your site. This could be a compromise.
Interesting. Yeah. So come visit. We can show you pictures of what it was and what it's like now, and
But now the problem is that I must come twice, in winter and in summer.
Maybe you don't want to.
Lorraine, sorry. Lorraine, would you like to go ahead?
Yes, I'm thinking too that a couple of questions. We have a lot of headlands that are mud and, a lot of fine sediment, pebbles, bigger rocks, and they are disappearing at an incredible rate. So that will be affecting what ends up on the beach as well, I'm sure. Yeah. We have lost islands entirely because of that. My question is, what do you use to measure? How do you take taking a sample is not a problem, but what do you use to do the observation and record what the diameters and stuff are?
Okay, I use generally for sand and gravel, we use sieves. I use sieves with half intervals, so many sieves, and so I dry the samples, I weight the samples, then I sieve them, and I weight each portion remained in each sieves. Then I create the gray sides distribution. We have seen them. After this, I use a program which we created it because the commercial program and also the program which are free for me are wrong. And I just sent yesterday paper to the Journal of Coastal Research explaining why this program, which is Gradistat, which is used by most of the researchers, is wrong because it extracts the values to create the curve in a linear distribution, whereas the original system was based on the probability distribution. Since the commercial program like Excel do not use the probability distribution, most of the people use this because they are cheap, they are easy, and so. And I make the comparison using the two systems, and there is some differences, not very strong, but there's a difference. However, this is a niche problem. I use sieves. I know that you will use comparators with the samples in boxes, different boxes, I think, and you compare them on the beach. You don't take samples and make analysis, I think. I don't know which is the accuracy, but I repeat that probably if we make some errors, the errors is when we sample the beach, because we have seen how much different there are samples, how much there are beaches sand in the different part of the profile. So even if there is a little accuracy in the analysis, I think that this is overlapped, is minor than the error we make in taking the samples. However, I think that I don't know if you have a sieving machine. It's cheaper than the instrument you have, but I think that in some cases you can compare using some laboratory, compare the error you make with the system you use with the other one, which is the standard system in sediment studies, mostly in coastal sediment studies.
All right. And speaking of, I guess, collecting samples, Veronica asks, how deep do you have to sample to get a profile of the changing part of the beach?
I generally, since taking samples, not only in the dry beach, but we take sample down to the depth of closure. This means in our coast down to 8-10 meters water depth. So when you have seen the studies in those bays, the bay is, let's say, 1 kilometer larger, and I take 100 samples. So it's very expensive taking samples with a boat, positioning with GPS and so, and making analysis. So we cannot repeat very frequently. We have done some monitoring in which we are sampling every 6 months. I don't say winter and time. We are every 6 months, and we compare it and we saw the difference. However, it's a very big problem. I wrote many years a paper which was rejected because I was confuting the theory, the standard theory, and I called those beaches anarchic beaches because these beaches were not obeying to any law which was considered the standard in sedimentology. obviously the director of the journal, which was sedimentology, was one of these leader in the field, and the paper was rejected. I published in another journal. However, the concept of anarchic beaches is exactly what I feel. They are not exactly anarchic, but there are so many laws to which they must follow that for us it's very difficult to find a solution and do forecast. I say that I don't have a way to characterize a beach from the sedimentological point of view. I call this a granulometric signature of the beach. It's easy to do that where you have kilometers of beach with very fine sediments, all almost the same from the dunes to 10 meters water depth. These are not the beaches in the Mediterranean, they are not the beaches in your coast. And so to find a sediment which is can be used to classify that beach, I think it's almost impossible. We must find an approximation if you want to work, of course. It must be reasonable. We must admit that we cannot know everything, and we must find the best solution, which is really a compromise.
All right.
Yeah, thanks.
Thank you so much. Yep.
Oh,
Go,
yeah.
go ahead.
Sorry,
Sir.
Ravi.
No, go ahead. Go ahead, please.
Oh, yeah, thank you. No, that's because now we're curious about the methods. I just would like also to, I think it's the right moment to make an announcement for ESCOM, to all of us, is that the purpose of to have this presentation today, and to have an expert like Enzo here with us, is because, this question about how to measure the granulometry is not easy, just as I was just counting the time and the cost that Enzo just described, that we need to go to the beach to take a sample, to use different diameters, to separate later you need to dry and to wait. So this is a lot of work if we want to have exactly the value. But the idea in citizen science, that this is why we are a citizen scientist network, a citizen science network, is that also we can have, maybe this is not the tile analysis, but we can have some methods. The thing is that we have methods for many different parameters, but not for granulometry. So what we are launching today, this is something that is a news for everyone in ESCOM, is that now we have a full set of very short videos that we created to learn how to measure, to understand, of course, but also how to measure the granulometry. Now we're going to have this card we call the comparative card technique. This is based on a similar card that was created, or at least used in Argentina for geomorphologists from the University of Mar del Plata. So we just adapt to our condition here in Nova Scotia. And as you can see here, we can measure the size, the diameter. Of course, it's not really easy to differentiate from 0.06 millimeters to 0.1 millimeter. Of course, we just say that it's very fine sand. The idea in citizen science is not to be very accurate, is to at least have some information and that we use the same method. And we go to very coarse sands. This is in our scale, a very coarse sand, not in the scale that Enzo showed that the geomorphology they are using. But this will be an idea that we can differentiate how much fine is the sand. And also we have here in the cards a ruler, so we can also measure the general size of the gravels or the pebbles. But also we can define how sorted, and Enzo was explaining about that, how the sediment is sorting in the beach. So we can measure if it's poorly sorted, is that it's almost the same, that size, moderate sorted, or well sorted, so that you know, the difference between the different sizes, and also the shape, because it's not the same what is angular, what is rounded. It also gives information to us. So this comparative card technique is the card that we expect to start using from our monthly monitoring in May. This is why next month in April, the Saturday the 11th, we will be in the south part of the ESCOM area, and in the 25th will be in the north part, the ESCOM area. We will be explaining to you how to use this comparative card technique, and with the plan that in May we start having our own data about granulometry. And also, I think it will be very timely if Enzo decide finally to accept my invitation to come here to Nova Scotia this summer. We can also use this card with Enzo.
Enzo, you're muted. Just letting you know.
Yeah, I have a similar card, and there is also a firm that sells, or it was selling, a set of sample of different dimension in small boxes, transparent boxes. I also made this. I sieved a very unsorted material. I selected a small sample for each sieve, and I put in a box with a glue to attack them, and I have a three-dimensional, a real card like that, and we generally arrive to reasonable results. But again, because I think that there is a so strong variability of grain size in one beach, that the error you make in the analysis is, however minor, compared to the error in sampling, at least this in mixed sediment beaches. So why spending time and money to make very accurate analysis in a sample when you know that this sample is not reliable? This is the problem. So I think that you will have good results also because with this system you can make much more analysis than what we do. So you can compensate the reduction in accuracy with a high number of samples.
Thanks so much. All right, any more questions? If not, I think we'll bring this really interesting webinar to an end. Thank you so much, Enzo, for coming to talk to us about granulometry. I think for sure I was significantly, over the course of your webinar, I became more and more excited about granulometry, especially more than I was before it. So I'm really excited to start seeing granulometry used and monitored as a part of ESCOM. We, of course, invite you to Nova Scotia to come see our beaches.
I will come.
Of course, of course. Thanks so much, everyone, for attending. This webinar, once it's been recorded, will be posted on our YouTube channel. If you just search up ESCOM webinars on YouTube and click on the ESCOM webinars 2026 playlist, you should be able to find it there. So feel free to check it out. Feel free to check out any previous webinars. Thanks everyone for coming, and have a wonderful evening.